So previously we've talked about thermodynamics, thermo meaning heat, and we did a lot of calculations involving heat and whether a reaction would be endothermic or exothermic. Now we're going to see that there are actually other factors that will affect whether a reaction is going to occur or not. So we've talked about the first law of thermodynamics. We said that energy cannot be created or destroyed, and that the energy of the universe is constant. Now, energy can be changed. It can change in physical or chemical processes. But the amount of energy is going to be constant. So for example, if an ice cube is melting, the ice is going to absorb energy. That energy has to come from somewhere. So the surroundings are going to lose energy, but our energy is going to be constant. Now, when I say that a reaction is spontaneous, I mean that it's going to occur without outside intervention. So if I put an ice cube out on the table, it's going to spontaneously melt. I don't have to do anything to it, it just happens. Now when I say it's spontaneous, I mean that it happens. I don't mean that it'll happen quickly. I don't mean that it'll happen slowly, just that it will happen, okay? Now for example, if I leave iron outside, it will eventually start to rust. This happens spontaneously. It's not going to happen in a matter of seconds or minutes or even hours, but it will happen on its own without me doing anything to it, okay? So that's spontaneous. Now, when we're doing thermodynamics, thermodynamics tell us the direction that a reaction proceeds. It does not tell us how quickly or the speed of the process. I know that my ice cube will melt if I leave it out on the table. It will not suddenly refreeze, so I know the direction, but I don't know how quickly it occurs, okay? The rate we talked about previously, remember, rate depends on activation energy. The higher the activation energy, the slower it's going to be. It depends on temperature. The higher the temperature, the easier it is to achieve activation energy. The faster molecules are moving, the more energy they have. Concentration, the higher the concentration, the more likely my molecules are to find each other, the more likely they are to react. And catalysts, which lower the activation energy. So all of these things affect rate. Spontaneity is not rate. Spontaneity is not speed. It just says that it will happen. Now, when I'm talking about thermodynamic data, I say that I only care about the initial and the final state. It is a state function. So we've talked about state functions before. Remember, in a state function, if this is my initial step and this is my final step, I could go the direct route. That's one way to get there. Or I could take a different path. A state function says, I don't care what happens in this middle part. I only care about where I start and where I end, okay? Now, when we talk about thermodynamic data, it's going to tell us that a process occurs in one direction. Now, we've talked about this before. When we talk about direction, the example we keep using is ice. Below 0 degrees Celsius, water will spontaneously freeze. My ice will never spontaneously melt below 0 degrees. It goes one direction. At temperatures above 0 degrees Celsius, my ice will melt. It will never spontaneously refreeze, Okay, so when we're talking about thermodynamics, it's telling us whether the reaction is spontaneous or not, and which direction it's spontaneous. Okay, now we've talked about enthalpy before. Now we're going to talk about something new called entropy. Entropy is represented by this letter S. Now, when we talk about whether a reaction is going to be spontaneous or not, there are several factors. One is going to be whether the reaction is endothermic or exothermic, enthalpy. One is going to be temperature, and the third is entropy. Entropy is a measurement of randomness or disorder. Okay, so systems are favored if they are going from order to disorder, or if my entropy is positive. If I have more disorder, it's going to be favored. So think about it this way. If I have a deck of cards and I throw them up in the air, they're going to scatter. More disorder, that's favored. There's a slight possibility that if I throw them up in the air, they'd come back completely evenly stacked. But that's a very, 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 very small chance because disorder is favored. Randomness is favored. Okay? So when we talk about entropy, there are lots of factors that affect entropy. Okay? So let's look at our gas. Okay? Remember that we said in a gas, our atoms or our molecules are spread out. They are in continuous random motion. Okay? So we said that they're going to travel in a straight line until they come into contact with something. They'll change directions, and we say that the change in speed is going to be basically negligible. So they're just bouncing around. Gases have very high entropy, high disorder. Okay? Liquids, if we look at our liquid, they're going to have much smaller kinetic energy. Here my gas is moving around, bing, 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 bouncing all over. My liquids are moving. They're sliding past each other. However, they've got these attractive forces. Those attractive forces are holding them together. They slide past each other, they move past each other, but they're still in contact. We said our gas, the volume can change depending on the size of the container because there are no forces between those molecules. Our liquid has those forces. Because it has the forces, there's a lot more order, so the entropy in a liquid is smaller than the entropy in a gas. Okay? Now solids have even lower kinetic energy, and they're going to have very strong attractive forces. Okay? If I look at my solid, everybody here is all lined up, neat and organized. Everybody has their place. They're holding on to each other really, really tight. Now there is still some disorder. These molecules are not 100% stationary. They're vibrating in place. I've got electrons, I've got protons, I've got neutrons moving around as well. I've got all of my atoms around the central atom if there are molecules. So everything still has some disorder, but it's going to be much smaller than a liquid, and a liquid is going to have much less disorder than a gas. Okay? So state is one factor that affects entropy. Okay? Now let's say I mix two pure substances. So I take salt and I mix it with water. Anytime I mix two pure substances, the entropy is going to increase. So I'm going to have a positive value for my S. So if I had my solid salt and I add it to my liquid water, all of my salt ions, my Na plus, my Cl minuses, are going to spread out among the liquid molecules, and so I'm going to create more randomness or more disorder. Okay? So, changing state, mixing things. The third one is going to be increasing molecular complexity. Okay, so here I've got methane, 1 carbon, 4 hydrogens. The S is going to be 186.3 joules per mole. Ethane, 2 carbons, 6 hydrogens, 229. Not quite double, but almost double. I have more atoms. They're going to be able to vibrate more in place. I'm going to have more protons, neutrons, electrons moving around. I'm going to have more things shifting, so it increases as I have more atoms, a more complex molecule. If I move up to propane, now I've got 3 carbons. I've got 8 hydrogens, even more complex. I go from 229 to 270. Not quite as big a jump, but it's still a pretty big jump. More protons, more neutrons, more electrons, and these atoms are going to be able to vibrate in place. They're going to be able to shift around my central atom. I've got more possibilities for shapes, more randomness. Okay? The last factor that affects entropy is number of molecules. Now, this is going to be for gases. Okay? So, fewer molecules is lower entropy. Okay? So here, my nitrogen, I've got 1 molecule. I've got 3 molecules of hydrogen. So I have 4 different molecules over here. Over here, I'm making 2 molecules of ammonia. Now, I have a lot less stuff floating around. My mixture is going to be less random, so I've got lower entropy. Okay? So let's take a look at some examples. Okay? I want to circle the one that has higher entropy. Solid CO2 or gaseous CO2? I said that a solid, everybody's neat and organized. A gas, everybody's moving around. So my gas, is going to have the higher entropy. Okay? B, I've got N2 gas and N2 gas. So same gas, they're both gases. The only thing that changes is the pressure. Well, let's think about our gas. If I have more pressure, I'm going to be more squished together. I'm going to be less spread out. I'm going to be less random. If I have less pressure, everything spreads out, and so it's going to be more random. Okay? Change in volume only affects gases. Because remember, my solids, my liquids, my gas, or solids and liquids, the volume doesn't depend on the shape of the container, the size of the container, but because my gas can spread out, it can become more random. Okay? Solid iodine or iodine dissolved in water. Here I've got a pure substance. Here I have a mixture. Mixtures are always more random. Okay? Let's look at D. Iodine vapor or liquid iodine. Go ahead and take a second and circle the one that's going to be more random. A vapor or a liquid. Okay? Take a second. Circle O2 or O3. Which is going to be more random? Now, F and G, we're looking at chemical reactions. So we want to look at whether our reactants or our products are going to be higher entropy or lower entropy. So for example, in F, I'm starting with one molecule, and it's a solid. I'm changing into one molecule, which is also a solid. That doesn't affect it. But now I've got one molecule that's a gas. Because I have more gaseous molecules, my products are going to have higher entropy. So take a second and solve G. Which side has more randomness, my reactants or my products?